Okay, good morning. Today our lecture is on production and uses of X-ray. Okay, as I'm making the lecture available on YouTube, you may find getting ready to go over review. Okay, as I've said, I'm making my lecture available on YouTube so that those who don't have a Facebook account can have access to it freely. More to help you. So as I'm new in this area, you'll find that the best way to look for my lecture is to go under my name, right? Woo Hin Koo. Then you can get it. You Google, like for example, photoelectricity, you will never find me there because there's so many lecture on photoelectricity. So if you want my video, you have to look for my name, Google, YouTube, my name, then you can find it. Okay, let us carry on with our lecture. Okay, under your syllabus is 25.6, production and use of X-ray. Right? We divide the three different video. Part 1 will be production of X-rays, how it's produced. Part 2, we call diagnosis, use of X-rays. And then part 3, CT scan. Right? What are we going to cover? Principle of production of X-ray. How do you produce X-ray? Main feature of X-ray tube. X-ray imaging. That's a part 2 already. Right? Uses of X-ray. Sharpness and contrast. What is sharpness and contrast? And then absorption by substance. When we say substance, it's more of your body tissue. That is the formula we introduce. And then the purpose and principle of CT scan. Understand how an image of an 8-pore cube can be developed. Usually they use 4 rather than 8. I don't know why the syllabus still want to use 8. Okay, you can use this reference book or any other book. You find it helpful. Okay, you can find in our library. And then past year paper, page 211, page 215. Right. Let me just try to do a bit of motion. Just a bit of delay. Since we are going to be on YouTube, just show you where you can get my notes freely. Those who want to follow up. Okay, just give me a few minutes and we will carry on with that. Okay. For those who want the notes or the PowerPoint or the video, you can go to this Facebook page, A-Level P6 A2. Okay, and you can get there's the notes there, and PowerPoint. Okay, that's the PowerPoint that we are doing. The video will be posted later. Okay, So let us carry on. Right? Just go a bit of introduction to remote sensing, right? Or another way of saying is non-invasive technique of diagnosis in medicine. Right? Non-invasive, it doesn't go into your body. It just put a device outside to see what's inside your body. Right? Remote sensing may be described as some form of investigation of an object using equipment that has no direct contact with object being investigated. You have to look inside the body, yeah, and any tumor. You put an object outside, an equipment outside, to see what's inside there. You don't have to break the body up. Right? Example, you can also see a satellite orbiting the Earth, right? Designed to detect small changes in mean sea level. It doesn't have to come down to check the sea level, but it can far away can detect these small changes, can be interpreted to determine the nature of the rock under the seabed. The investigation enables information to be gathered without actually drilling into the seabed. That's a benefit. Just like a human body, I don't have to do the surgeon doesn't have to do the operation to see what is the tumor inside there. Right? That is very traumatic. He can just uh, use this device or equipment to look what's inside the body first before he cut it up or open your skin or dissect. Okay? So that is the purpose of remote sensing. You don't have to be on the ground. You can observe it from far away, above the earth. Right? Traditional diagnosis, you see a doctor, I don't feel sad, really. Right? You have to tell the doctor what is happening. Just sort of empty. And the doctor will probably listen to you. What's wrong with me? Well, doctor will say, your me count puts you in the 17th percentile for self-absorption. He will diagnose, and then he will try to tell you, and you are tested positive for stopping for a minute while putting on your shoes just to stare at your feet. So he will evaluate, or he may test you, and then he will give you an answer. What is wrong with you? So it depends very much on the experience of the doctor. Right? So historically, observing the patient outwardly for signs of fever, vomiting, change breathing rate, etc. And this depends greatly on the experience, but was still blind to detailed internal condition. We cannot see what is wrong with you internally that's causing the symptoms outside. So it depends a lot on the experience of the doctor. The other alternative is to observe the patient inwardly by surgery. Cut you up, open your, you got a lung tumor, open up your skin and then look into your lung. This technique leads to trauma. Some people don't like operation, and sometimes death to the patient. Because it's something we all don't like. Very frightening. In earlier time, it can also have operative infection. Just like when I was having a operation for my hamstring transfer, they are hoping that by transferring the muscle at the back of my knee to the front there, they could help my polio. One of the patient there has been there for, I think, 6 months. The wound doesn't heal, keep on infecting. So that is the danger of surgery. Modern diagnostic technique have concentrated on using external devices or equipment to see what is under the skin. X-ray, ultrasound has been used in cases of pregnancy to see how the baby is developing, boy or girl. Magnetic resonance imaging is now becoming frequently used technique. Right? This one we are not interested in. Right? Technique involving laser, that one we are not interested in. A, B, C, this one is interested in A-level syllabus. Aim is to obtain detailed information. Diagnostic is not enough. You want to know what is happening in your body that causes the symptom. Right? You want detailed information concerning the internal structure. Right? Is there anything abnormal in the organ? Right? We don't want surgery. Right? We want surgery. And this type of device, this type of method is called non-invasive technique. I don't invade your body. I don't open your body. No surgery involved. Okay, let's look at part one, production. The note is on page 315. One, non-invasive. Right? Non-invasive techniques are designed to present a much smaller risk than surgery. Surgery, there can be infection. As I shared with you, one of the patients have been in 6 months there. The wound doesn't heal. There's still pus there. The doctor cannot let him go off. Whereas for me, my surgery after 2 weeks, they see everything was okay. They say you can go home and come for monthly check. That's traumatic. The wound there sometimes can be painful and you can hear sometimes patients who come for operation, especially the handicap, polio, the leg, somehow or other the leg is not properly curl up, so they have to stretch it to straighten it, and you can see the patient screaming in the middle of the night. A medical procedure is strictly defined as non-invasive when no break, you don't do any surgery. Break on the skin is created and there is no contact with the mucosa or skin break or the internal cavity beyond a natural or artificial orifice. Right? Either you don't cut the skin, you may put in the opening in the mouth there, they put some device there to observe what is inside your stomach. That's less traumatic. X-ray or X-radiation, right? The range of wavelength 10 to the power minus 11 to 10 to the power minus 9 meter. Frequency is about 3 times 10 to the power 16 to 4 times 10 to the power 20, very high frequency. So that's why we define X-ray as very high frequency. High frequency corresponds to small wavelength. Right? High frequency, same as high energy, electromagnetic radiation. Right? Remember, we are thinking of X-ray as photon. E equals to HF. Right? E equals to HF. High frequency means high energy. It's produced when charged particles, usually electron, moving at high speed, are slowed down rapidly by striking a target. E is slowed down when the electron strike the target, and then X-ray is produced. Let's just summarize for you. And this is for info. Right? Being used in the world, detecting cover painting. Some people may frighten that a precious painting may be stolen, so they just cover it up with another layer of painting there. Right? For engineering, check metal casting for defects, crystal analysis. Right? We are more interested in medical uses. As well as application of what we have learned in quantum physics, diagnostic, detection of broken bone or tooth cavity. And then sometimes we may add absorber, barium or iodine. X-ray may be used to check respiratory or digestive disorder. Just like when I was in New Zealand, every time when I see doctor complain about stomach problem, and they have two very serious food poisoning. They have to vomit it and then feel better. And then partly drinking milk, right? Our body, we cannot. Milk is cheap in New Zealand, so we drink milk. And about 3 to 4 o'clock, the stomach will start to make noise. And then a lot of farting. You go to toilet, you farting, liquid come out. So of course, this one is very uncomfortable when you are studying and then all this noise. So you see a doctor. Right? That time it was free. The doctor couldn't find the problem. See him so many times. Then he gave me antacid tablet. So finally, he sent me to Wellington Hospital to have an X-ray. So they gave me a milk with barium, and then that's how they see nothing wrong. Right? So the only thing I can say now is probably due to milk. Most of us Asian cannot drink milk after a certain age. Well, the other uses with therapeutic treatment of malignant cancer, which we are not interested in that. Right? Some of the things that we will be using again, right? Where we have a charge accelerated to a potential difference of V. Right? The gain in kinetic energy of the work done is QV. Right? That's the definition of potential difference. Work done divided by charge. Then intensity is the rate of energy falling normally per unit area per second. Same. Your AS work. So the greater the rate of energy P falling on the surface, the greater will be the intensity. Power divided by area, the X-ray falling on the surface. And the formula, right? Speed of wave or speed of light or speed of electromagnetic wave is just the speed of light, frequency times wavelength. Right? Continuously, we'll be using frequency is inversely proportional to wavelength where the speed is constant. Energy of photon, remember we think of X-ray as photon. So that is your Planck's constant. F is your frequency. Okay, function of components of the X-ray tube. Right, there's your X-ray tube. We have evacuated chamber. We want it to be vacuum so that the electron can go straight through, not deflected elsewhere. We want it to go straight through. Then the low power supply. That one. There's a low power supply, low voltage. And then there's your cathode, right? Connected to a negative supply. And we call cathode or filament. And then the high voltage or operating voltage, right? Connect your cathode, and that's your anode there. The voltage used can be 20 to 100 kilovolt. There's your anode. Positively charged. It's a positively charged, cathode, negatively charged. And then there's your target there. Right? So when we hit the filament or the cathode, the electron is emitted and strike the target, and then the X-ray is produced coming out of this window. There's your X-ray window. And then because a lot of heat is generated in the target, you want it to be conducted away. So yeah, then you have to cool the anode to carry out this heat. If not, the target will melt. Okay, let's look at the function of each part. Yeah, this provides the operating voltage. That means it accelerates the electron that's emitted, and is the one that gives the kinetic energy to the electron hitting the target. access the electron, and then the low voltage for heating the cathode. And it controls the filament current. That means the higher voltage, more current, and more electron will flow. So it controls the intensity. So if you like, you can think of intensity as number of photons that's produced. Okay? Because each electron will produce one X-ray. So that is your electron emitted from the cathode by the process called thermonic emission. You heat it up, the electron is emitted. It hits the target. The electron, right, or the current of the electron current determines the intensity of X-ray. So the greater, more current flowing into the filament, more electron emitted. So remember, each electron produces one X-ray. So the electron current determines the intensity of the X-ray. That's it, X-ray coming out. An electron, when they hit the target, decelerates and lose energy to the target. And the energy given, that is the maximum that can be given to the target, is depending on the voltage you use here. There's a charge on electron, there's a potential difference across the field. Okay, so this determines the maximum energy of the X-ray. Cannot go than that because you are the one who supply the operating voltage. So that voltage determines the maximum kinetic energy of the electron and determine the maximum energy of the X-ray. And usually 1% of the energy of the electron appear at X-ray. So it means that 99% of the heat is on the cathode. And if you don't get rid of the heat, it's going to melt the target and the anode. So that's the purpose of using a good conductor for the anode to conduct the heat away. And then you must have a proper cooling system to get rid of the heat. Some use cooling fin. We will look into that later on. Heat produced by decelerating electron radiated as heat. Must get rid of the heat. Okay, we look at concentrate a low voltage source for heating the cathode. Right? So it controls the filament current in the tube. It also controls the intensity of the current. Electron current that's flowing to the target. Anode is positively charged by this power supply there. Made of solid copper. Why copper? Because copper is a good conductor of heat. A lot of heat is generated in the X-ray tube. About 99% of the energy of electron is converted to heat. So the anode is positive, cathode is negative. So this operating power supply accelerates the electron from the cathode to the anode. And then it hits the target that usually made of tungsten. Right? Why tungsten? It has a high melting point. And heavy metal. Nuclide interacts strongly with the bombarding electron to produce X-ray. Okay, the cathode, negatively charged. Right, and it is all connected to the anode with the operating, with the power supply. So this V is usually high, provide a high potential difference. So electron is emitted by the heating of the cathode by this low power supply. Electron emitted accelerated to the anode. Right? That's the purpose of the high voltage unit to accelerate, and it's very dangerous, this high voltage unit. Right? It's our source of high PD, high voltage unit of external power source, right? And it applied between the anode and the cathode. Provide the operating voltage. Accelerates the electron to high energy. As we have said, the maximum kinetic energy is EV. Then cooling fins, like in your refrigerator at the back there, you see the cooling fins there. Right? As the purpose is to let the hot heat that is absorbed from the refrigerator to let it go outside to the atmosphere. Right? Heat generated at the, so in this case, the heat generated cathode is conducted along the anode to the cooling fin. And the cooling fin radiate away the heat. Right? This is the old traditional method, use cooling fin. Modern method use a rotating target. Means you use one side of the target and you rotate to another side, then rotate to the side, and give it time to cool down. Rotating target allow different parts of target to be used as the target is rotated, and so the part that's not being used irradiate energy emitted. It allows to cool. Other methods of cooling, you don't need to know all this. These are just extra knowledge for you. Right? You can, the older one is you use water, right? Because water absorb heat. Right? So these are various methods that we use. You don't need to know too far. Some use water to cool the target. Right? Water flow to the cooling fin. Water because water absorb heat. Energy of electron. We have already indicated. Since the majority of the energy of the electron is transferred to thermal energy in the metal anode, the anode is either water cooled or made to spin rapidly so that the target area is increased. You don't use one single area. If you use one area, you heat it up. So you use one time and then you spin it, another part is used, and you spin it fast, it will cool. Right? The heater part will cool down. Okay, energy of electron, kinetic energy of electron on reaching the anode or the target there is EV. Right? That's the work done to accelerate the electron from the cathode to the anode. V is the operating voltage. This one. Not this one. This one is supplied for heating the filament to produce the electron. So energy of X-ray, that is your kinetic energy maximum coming into the metal target there. So this energy of the X-ray that's produced. Right? Remember, not all the kinetic energy electron goes to produce the X-ray. F is the frequency, H is Planck's constant, and then EV is your work done on the electron or the kinetic energy electron. Q is the energy given to the target. Right? Q energy given to the target. EV is the kinetic energy of the electron. So the maximum frequency of emitted X-ray is where there is no heat given to the target. That is where we get our maximum frequency. Okay, maximum frequency when all the electron energy is given to produce the radiation. Remember, maximum frequency means minimum wavelength. Right? We are just using this formula. Lambda is inversely proportional to frequency. H is Planck's constant, C is the speed of light. Accelerating voltage. Electrons emitted by the heated cathode, that's the heated cathode. Right? The accelerating voltage, that's the accelerating voltage, different author will draw it differently, but it doesn't matter. Right? Accelerate to the target there to a large potential difference. This is usually very high potential difference. Right? 20 to 100 kilovolt for diagnosis before bombarding the metal anode. The X-ray produced leave, so the X-ray produced will leave this There's a window for the X-ray to leave. Intensity, right? Or we call it tube current or electron current, electron beam. Intensity of X-ray beam is determined by the rate of arrival of electron. It at the metal target, or we call the electron current your tube current. Thus, intensity of X-ray beam can be considered as number of photon or specific energy emitted per second per unit area. I don't need to go too far because usually the beam have a particular area, so a particular size or area you will hit the surface. So when you think of intensity in this part, you just think of it as number of photon, number of particles that's produced. Easy to understand rather than think of it as is correct number of photon or specific energy per second per unit area. Just think of it as number of photon per second. Okay, so that summarizes for you where we obtain this form, show you the formula in quantum physics. Right? There's a number of photon, there's the energy of the photon, there's the area that the X-ray beam fall on, and that's the time. Right? So the tube current, right? This is the tube current, electron or the electron beam is controlled by this low voltage source. The greater the heater current, hotter the filament, and hence the greater the rate of emission of the electron on the filament. X-ray spectrum, of course, before we can send the X-ray into the human body for diagnosis, we need to know the X-ray spectrum. What are the different frequency? What are the different wavelength? Not every wave frequency is beneficial for the human body. Okay? So basically, the X-ray that emerge from the X-ray tube have a range of energy, right, as shown by the what you call spectrum. So we have encountered absorption spectrum before, under energy level, quantum physics, and then continuous spectrum. So this is your X-ray spectrum, right? Can be intensity against wavelength. X-ray spectrum consists of two components. A curve showing continuous distribution. That's a curve. Continuous distribution, that one. Right? That means all this wavelength from the smallest to the largest. Right? That's a distribution. And there's a sharp cut off of short wavelength. Right? Remember, higher frequency or short wavelength. And a series of high intensity spike. That series can be 2, can be 3. Right? High intensity spike. Sometimes it's just here only, you don't have that one. It doesn't matter, depends on the metal you use. Right? As we said, characteristics of target material. So if you use tungsten, you will see different spikes than you use other metal. Right? So we have intensity, we have wavelength. That's our graph. Right? As I say, it's easier to think of intensity as the number of photons of X-ray emitted per unit time, per unit area. Okay, so that's your continuous distribution, right, of energy for all the different wavelengths. Right? You should be able to explain that. Why? Why do we have this continuous distribution electron? When we, right, the accelerating electron, when they hit the target, when it decelerates, it gives out energy. It doesn't have to give out all. It can give out different amount as he wants. Right? So that's why we observe it as this particular shape, continuous distribution. Right? It gives out energy at different wavelength. So largest at this one, this wavelength. Okay. So these are all experiment observation. And then what causes this is a series of spikes Right? These are we call high intensity spikes. That means high intensity for a particular wavelength. And then we have a sharp cut-off wavelength or minimum wavelength or maximum frequency there. Right? As we have said, that sharp off we must be able to explain is because there's our kinetic energy of the electron. This is the X-ray that is produced. Right? No heat loss. All the energy that we use to accelerate the electron produce the X-ray. That explains why we have a short wavelength here or maximum frequency. Right? Remember, examiner is not going to just be restricted by a particular graph. They can draw intensity against photon energy. Okay, so you must be able to see it's the same as this one, right? Except we just turn the graph the other way around, that's all. Okay, it has a maximum frequency or maximum energy. Right? It can be energy, photon energy, or it can be frequency, same thing, maximum energy there. Okay, so that is a maximum frequency there. So we have already explained this is stress. When the electron strikes the anode, it will be attracted towards the nucleus of an atom in the nucleus. This will cause it to change both speed and direction. Right? Or we call it decelerate. General term we use acceleration, but right, in particular is decelerate. Right? It comes in here primarily, it decelerate, right? It's being attracted, then it's scattered, then you have your X-ray being produced. A decelerating electron loses energy by emitting electromagnetic radiation. In this case, the electromagnetic radiation is your X-ray. Primary electron beam, scatter electron. And you have your continuous X-ray. Right? We call this breaking radiation. Okay, EK max, maximum kinetic energy, due to your accelerating voltage, it will reach the target. Right? There's a large deceleration occur, and the radiation produced is your X-ray. It's the X-ray part of the electromagnetic spectrum. Since the electron have a continuous distribution of acceleration, they can give any amount. Right? They don't have to give all of it. Right? Can give from a small value to the largest value or maximum energy. That's why we have a continuous distribution of energy for the wavelength produced. Okay, so we can represent it as kinetic energy, photon of X-ray, plus energy given to the better target. And where none is given a target, then there is your maximum frequency. Okay, so these are various formula you can play with. F max, and take the h down, you get this equation, and then remember you can convert it to wavelength. Cutoff wavelength is the minimum wavelength of X-ray emitted at a particular operating voltage. This corresponds to maximum energy of the electron given to the target. Right? So at the cutoff wavelength, all the energy of the electron is given to produce the X-ray photon. Okay, that's how we get that minimum. Okay, formula, combine all this formula to get that. Right? So to summarize, no power supply, heats up the filament, and it determines the intensity of the X-ray. Electron track the target, The larger energy, higher will be the energy of the X-ray. So higher energy, remember, shorter wavelength. So we expect the X-ray coming out will have a range of wavelength from minimum to maximum value. Remember, there is a cutoff wavelength there. Depends on the operating voltage. As we say, this formula will be for you. Independent of the material. If it's tungsten you use, it will always have a minimum wavelength. And that minimum wavelength depends on your operating voltage. E is the same, C is the same, H is the same, constant. Sharp spikes are high intensity peak, consist of groups or series of 2 or 3 superimposed on the continuous spectrum. Location of the spike depend on the material of the target or characteristics of the target material. It means the spike will tell you which particular metal they are using. So as the voltage, operating voltage increases, the spike doesn't change. The position of the wavelength doesn't change. It remains the same. Okay, so there are the series of curves we can draw at different potential difference. Series of spikes at your cutoff wavelength. We only see spikes when the operating voltage is above certain value. And then the spike is characteristic of the material you use. Right? And then you must know right, what causes the spike. Because your electron have enough energy to knock off an electron, inner shell electron. And when the electron from further up the shell comes out to fill the space, then X-ray is emitted. Emission spectrum. As we have said, for the spike to appear, the curve, the operating voltage must be sufficiently high. For example, for tungsten, it must be greater than 72.8 kilovolt. And we just summarize. This peak corresponds to emission line spectrum of atoms of the target. The electron that bombard the target knock out the inner shell electron, and the subsequent the excitation electron from nearby shell give rise to the line spectrum. Okay, so this one just summarize for you, this diagram. What we have just learned. Right, you can treat it as a mind map to summarize what we have learned. Okay. Okay. How we produce our X-ray. 1% of the energy of the electron is given to the X-ray. And then the metal is to radiate the energy away. And then you must be able to, the spectrum, identify what causes the minimum wavelength. And then this is a continuous curve distribution, how to explain that. And then series of spikes, how to explain that. Okay. So this is because of the kinetic energy given completely to the metal, produce the X-ray. Right? And the spike is due to electron transition from higher energy level to lower energy level. And then the continuous distribution is due to electron accelerate as they give different amount of energy to the target metal. Okay, I think we have completed. Okay, we have completed. The next part 2 will be uses. So we end zoom here. Right? Hope to see you the next one, part 2.